So we have a circle. It can have, oh, my video just like paused. Sorry. Okay, we have a circle and it can have any radius. Often we talk about a unit circle that has a radius of 1, but really the radius can be any positive number. And the idea behind what a radian is that it's an angle. Specifically, 1 radian is the angle you get if you take the length of the radius along the circle. So if the arc length, right, if this length here in green, if the arc length is equal to 1 radius length, so I'm saying that this length here and this length here are the same. If the arc length is 1 radius, then the angle subtended by the arc. Now that's the word, I'm not a fan of the word subtended. I was like, what is subtended? So when you have an arc length here, the angle that goes with it, that's the angle that's subtended by the arc length. If the arc length has a length of 1 radius, then the angle has a measure of 1 radian. That's it. Literally, the angle here is how many radius is, or how many radii is the correct way of pluralizing radius, but I still say radiuses is. The angle here is just how many radii lengths it is subtending. So if I wanted to, I could go another radius worth over to like here, and this angle, meaning this angle here, which I will call, I'm also going to call theta, but it's theta in blue. That angle there, well, since this length is 2 radius lengths, that angle is 2 radians. I will also point out, because this, why does it say after arc length and before? It says S. So typically it says arc length colon S equals 1 radius. S is often the variable we use for an arc length, whereas lowercase r is often the variable or the letter we use for radius. So that's all good. I'm just writing S. So this angle here would be 2 radians, and I will tell you, oftentimes people don't say radians. I could also just say the angle is 2, because we know that if there isn't a degree on it, we mean that it's a radian measure. So if someone means degrees, they have to write the degree symbol. If someone means radians, they usually don't say anything. Let's talk about going all the way around the circle. We know the circumference of a circle is 2 pi r, right? It's literally 2 pi radians, or I should say, sorry, it's 2 pi radii, right? The length around the circle is 2 times pi times whatever the radius length is. So if the length around the circle is 2 pi radii, or 2 pi radiuses, then the angle around the circle is 2 pi radians. Again, right, the angle is just how many radiuses does it take to go all the way around that angle measure? Well, all around the circle, 2 pi radii, the angle, 2 pi radians. And then I also wrote over here, 1 revolution, which is just what we're saying, is 360 degrees, and it's equal to 2 pi radians. So this is a very common thing to make note of. 360 degrees and 2 pi radians are equal to each other. In the same sort of way, 12 inches, I was going to write feet. In the same sort of way, 12 inches equals 1 foot, right? They're equal, but they have different units on them. These are equal, they have different units on them. This is in degrees, this is in radians, but they're still equal to each other. Okay. So again, let me, for those of you that weren't here before, let me throw up these videos again. If you want, you can take a moment and watch any one of those. They do a good job as well of explaining how radians work. And their visuals are maybe a little better because some of them are like, they're all, I think, computer generated, so their lengths are exact as opposed to mine, which are approximate. Okay, but this is the idea that we're going to take with us to convert between degrees and radians. So typically, instead of saying 360 degrees is equal to 2 pi radians, if you want, although we're going to mostly not write the radians in, you can divide both sides by 2 and say that 180 degrees is equal to pi radians. Sometimes we abbreviate radians with rad. Definitely on a calculator, if you're going between degrees and radians, degrees is DEG, radians is RAD. And then you can divide both sides by pi to get 180 over pi is equal to 1. Or you can divide both sides by 180 degrees to get 1 is equal to pi over 180 degrees. So I want to point out that it's okay to multiply by this number because it's just 1. Just like if you're changing inches to feet, right? If I have something that is, I don't know, 42 inches, I can multiply that by 1, right? 1 foot equals 12 inches, so 1 foot divided by 12 inches is just 1. I can multiply this by 1. I can cancel those units, and now I get 42 over 12. And I can reduce that. That 42 over 12 is 3.5. This is 3.5 feet. So to change from degrees to radians, we multiply by pi over 180 degrees. To change from radians to degrees, we multiply by 180 degrees over pi. The way I always remember what to multiply by is the thing that you want to end up with should be in the top. And the thing you want to get rid of should be in the bottom. So if I want to go from radians to degrees, I should have degrees on top and radians on bottom. If I want to go from degrees to radians, I should have radians on top, degrees on the bottom. Okay, so that's kind of the setup. The great thing, maybe not the great thing, but the good thing about this is actually converting from radians to degrees is pretty straightforward. So we can convert the following from degrees to radians. Let's do a few. Let's do 30 degrees, 120 degrees, 90 degrees, 45 degrees. So for each of these measures in degrees, we're just going to multiply by pi over 180. I should say pi over 180 degrees to get to radians. This is going to be times pi over 180 degrees. And first off, the degrees cancel. And I'm going to rewrite this as 30 pi over 180. And then our job really is to reduce this. So we're going to write this, well, we can cancel the zeros, right? This is 3 pi over 18, which is 1 pi over 6, which is pi over 6. One unfortunate thing about the way we use the number pi is that this would be more useful if it was really written as 2 pi over 12. If I write it this way, I know that, right, 2 pi, that's a full revolution. So I've got 1/12 of a full revolution, which makes sense because 30 degrees is 1/12 of 360 degrees. So these are the same. This is 1/12 of the full revolution. This is 1/12 of a full revolution. This angle is 30 degrees. This angle is 2 pi over 12. But we write it as pi over 6 because it's good to reduce our fractions. So we typically do want to reduce our fractions unless, well, no unless we want to reduce our fractions. I'll point out 120 degrees here is 1/3 of a full revolution. So when I multiply by pi over 180, I'm expecting to get 1/3 of a full revolution, which is 2 pi over 3. Well, so you can cancel as quickly as you want. I'm showing more work, right? I would probably start right off the bat by saying, oh, that's 12 pi over 18, right? Cancel the zeros. And then 12 pi over 18, I can divide top and bottom by 6. That's going to give me 2 pi over 3, which is exactly 1/3 of a full revolution. 1/3 of a full revolution. Great. So these things are equal to each other. It's just that sometimes we prefer things in radians, sometimes we prefer things in degrees. I will also say we really do go back and forth in pre-calc and calculus. We need to be able to do both. Usually the default is radians, but we also use degrees quite a bit. So a couple more. This 90 degrees should be very easy to see, right? 90 over 180, I'm going to get a 2 in the denominator, right? This is going to reduce to just pi over 2. which is a quarter of a revolution, right? This is equal to 2 pi over 4. 90 degrees is a quarter of 360. Pi over 2, or 2 pi over 4, is a quarter of 2 pi. Then the last one here, 40. Well, in fact, we can go from 90 to 45 really easy. We know that half of 90 degrees is 45 degrees. So half of this should be equal to that. So I'm going to get 45 pi over 180. Right? Notice I'm not writing the degree symbol anymore. And then, I mean, it's going to be pi over 4. You can get there by, I see that 45 and 180 both are multiples of 9, right? How do I know that? Because 4 plus 5 is 9, and 1 plus 8 plus 0 is 9, right? That's one of the tricks for being a multiple of 9, that the digits add up to 9 if you keep adding them up. So 45 divided by 9 is 5. 180 divided by 9 is 20. And then 5 over 20 reduces to 1/4. So that's pi over 4. Or it's 2 pi over 8, right? It's 1/8 of a full revolution. So that's how you change from degrees to radians. And then to go from radians to degrees, we just go the opposite. The reciprocal, I should really say. Right, so if I want to change, say, I don't know, maybe pi over 10 or 5 pi over 4 or 4 pi over 3 or negative 3 pi over 5. So I will point out, most of the radian measures we're going to deal with usually have some pi. Right? We don't often talk about 1 radian or 2 radians or 3 radians because they don't have very nice degree correspond, right? 1 radian is approximately 57 degrees, but it's really not, it's exactly like, it's gross. So usually your radian measures will be some fractional multiple of pi. So pi over 10, we're going to multiply by, sorry, we're going now radians to degrees. We're going to multiply this by 180 degrees over pi, right? The unit I want on top. The pi's cancel. So I end up with 180 over 10. I should say 180 degrees over 10, which reduces to 18 degrees. Okay, same deal here. I'm going to multiply by 180 degrees over pi. The pi's do cancel. So I'm going to get 5 times 180 over 4. I would probably like to do some of the division first. So I know that 180 over 4 reduces to 90 over 2. And although I could continue, right, I could say 90 over 2 is 45. To me, it's actually easier to multiply by 5 and then divide by 2. Right? 5 times 45 to me seems hard. 5 times 90 is easy. It's 450. And then 450 divided by 2 is 225 degrees. And that's what we're doing, right? Just multiplying by 180 degrees over pi. Again, here the pi's cancel. So I'm going to get 4/3 times 180. Here I would do the division first. 180 divided by 3 is 60. So we get 4 times 60 degrees, which is 240 degrees. And that is definitely 2/3 of a full revolution. And this is definitely 2/3 of 2 pi. So it's 2/3 of a full revolution. And then this negative one here, what does it mean that it's negative? So when we measure angles, and I should have probably said this before, but it's all right. So when we measure angles, unless someone has said otherwise, we typically measure angles from the positive x-axis. So this, starting here, this is an angle of 0, either radians or degrees. And then this way is positive. So like this angle here could be something like, I don't know, 225 degrees or pi over 4. Sorry, 5 pi over 4 radians. But if you measure going clockwise, Then you have negative angles. So this angle could be something like, well, if it's what's left over, it would be 135 degrees, but it would be negative. So negative 135 degrees, or negative 3 pi over 4. So that's the whole thing with a negative angle. Positive angles, you go counterclockwise. Negative angles, you go clockwise. This one would end up being 2 times 180 degrees over pi. Pi's cancel. What's 180 divided by 5? I'm not good at dividing by 5, but I am good at dividing by 10. 180 divided by 10 is 18. But I divided by twice as much as I should have, so I need to multiply back by 2. So 180 divided by 5 is what is 180 divided by 10, which is 18, and then multiplied by 2. That's going to be negative 3 times 36 degrees. Yeah, 180 divided by 5 is 36. And then 3 times 36 is 90 plus 18, which is 108. This is negative 108 degrees. Okay. One last radian to degrees. What if we did have 2 radians? Well, 2 radians, if I want to change that to degrees, it's going to be kind of dumb looking, but it's going to be 2 times 180 is 360 over pi. And that is the actual answer. If we take 360 and divide it by pi, we get approximately 114.6. But this is the answer you should have. We don't want approximations unless people specifically ask for them. Okay. So that's how we change from degrees to radians and radians to degrees. So let's talk about some right angle triangles. I'm going to draw 2 of them here. So let's say we have this triangle and this triangle. I mean, they can look like whatever. I'm just trying to draw them kind of like they're drawn on the handout. And so we are interested in talking about an angle for these. So I'm going to call this angle theta and this angle theta. So there are 3 sides to a right angle triangle. The longest side is the hypotenuse. It's also the side that is opposite the 90-degree angle. So the hypotenuse is always opposite the 90-degree angle. I should also say the longest side is always opposite the longest angle, or the biggest angle. And then after that, there are 2 other sides. So there's the side that is next to the angle, and there's the side that's away from the angle. We call those the adjacent and the opposite. Here, the adjacent's right there, and the opposite. But I do want to point out that if we pick a different angle, right, if we pick the other not 90-degree angle, like let's say I draw a similar triangle there, but I'm looking at this angle now. For that angle, well, the hypotenuse doesn't change, but the opposite side is now this, and the adjacent side is now this. So which side is your adjacent and your opposite completely depends on which angle you have decided you were looking at in the triangle. Okay, so then we define the 6 trig functions. So there's the primary trig functions. There's sine of theta. So whenever you're writing a trig function, it has to be of an angle. So sine of theta, cosine of theta, and tangent of theta. I do encourage you to say sine, cosine, and tangent, not sine, cos, and tan. Don't say tan, say tangent. So sine is defined to be the opposite over the hypotenuse. cosine is defined to be the adjacent over the hypotenuse, and tangent is defined to be the opposite over the adjacent. And then you may recognize this gives us a mnemonic device people are maybe familiar with, SOHCAHTOA. Is the way people often remember that sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, tangent is opposite over adjacent. And then we have the reciprocal trig functions. The reciprocal of sine is cosecant of theta. So cosecant of theta is literally the reciprocal of sine. It's 1 over sine of theta. So if you take the reciprocal of sine, you get hypotenuse over opposite. And then secant of theta, which we abbreviate with SEC. Secant of theta is the reciprocal of cosine. It's 1 over cosine of theta. And it's equal to the reciprocal of that is hypotenuse over adjacent. And lastly, the reciprocal of tangent is cotangent of theta. And it's equal to the reciprocal of tangent. And the reciprocal of opposite over adjacent is adjacent over opposite. And there's no nice, I'm looking at this, there's no nice mnemonic device here. It would be cho, sha, cow. I mean, that seems like you could do that, right? If you really wanted, I don't think it's a good idea, but you could try for cho, sha, cow. Yeah, I don't know about that. I don't recommend memorizing that. It's not a good mnemonic device. It's kind of fun to say. So these are the 6 trig functions. You definitely need to memorize how they work. You definitely use these a lot in future math classes. They come up all the time. So you really want to know that sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, tangent is opposite over adjacent. And then the reciprocals. And the way I remember the reciprocals is that there are 3 co-functions that have the CO beginning: cosecant, cosine, cotangent. Each pair of thing and reciprocal thing has 1 cofunction and 1 non-cofunction. So the reciprocal of sine is cosecant. The reciprocal of cosine is secant. And the reciprocal of tangent is cotangent. 1 co and 1 not. 1 co and 1 not. 1 co and 1 not. Okay, questions about this before we start doing some examples? Erase the other side while I ponder for a moment. Okay, so then we're just going to use what we know about triangles, right triangles, to evaluate some trig functions of some angles. So let's say we have this very well-known triangle, which does not look to scale in the picture there, that's fine. Oh, okay, good job, James. There's the top of my triangle. Okay, we've got a triangle. The right triangle. And the side length here is 3 and the side length here is 4, and we're looking at this angle here. And I want to find all 6 trig values for theta. To be able to find all of the trig values for a particular angle, and I don't know what that angle is, right? It's just an angle. I mean, it looks like it's maybe bigger than 45 degrees, but smaller than 90 degrees. We don't need to know what the angle is. What I will say is we need to find the third side of the triangle. To find the third side of a right triangle, we should always be able to use the Pythagorean theorem. So the Pythagorean theorem, right? I'm pretty sure we talked about it in case we haven't. If you've got a triangle like this, where the hypotenuse is C, then we have the a squared plus b squared equals c squared. So if I want to find the third side here, I'm going to say that 3 squared plus 4 squared equals 5. Oh, I'm giving away the answer here. Equals c squared. And then we're going to solve for c. So 3 squared plus 4 squared is 9 plus 16, c squared. So 25 equals c squared. So c equals the square root of 25. You could have started by saying that c is equal to the square root of 3 squared plus 4 squared. But be careful, right? This is not 3 plus 4. That would be 7, but the actual answer is 5. And now we have all the information we need to find the 6 trig functions of this angle. By the way, this angle is theta. It's a Greek letter. It looks like an O with a horizontal line through the middle. It is the most common Greek letter used for angles, but we use alpha and beta and gamma also quite frequently. So let's see. Sine of theta. You do need to write the theta. If you just write sine, you're not saying of what. So really, when you write a trig function, the first thing you should always think after that is, oh, there's an angle there. There has to be some angle, whether it's a variable angle or actually like a degree. Like you could say, what's sine of 45 degrees? That's also something we will talk about. But here, sine of theta is opposite of hypotenuse. So it's 4 over 5. And cosine of theta is adjacent over hypotenuse, which is 3 over 5. And tangent of theta is opposite over adjacent, which is 4 over 3. Remember, we're looking at this angle's perspective. From this angle, the opposite is 4, the adjacent is 3. I always like to write those 3 primary trig functions first, because then I can write the reciprocal ones really easily. The reciprocal of sine is cosecant. Cosecant theta is hypotenuse over opposite, which is 5/4. Or just that one flipped over. Secant of theta is hypotenuse over adjacent, which is 5/3. It's also just the reciprocal of cosine. And cotangent of theta is adjacent over opposite, which is 3/4. But it's also just the reciprocal of tangent of theta. We'll also point out that sometimes you will have to use a calculator to find some trig functions of angles that are not here. So I just want everybody to be super clear. And actually, let me show you in the notes here. So I'll write it on the board. So I'm going to find the following 2 things and tell you. So what if I want to find, let's do the following 3. Sine of 2 degrees, cosine of pi over 5, tangent of 2, and cosecant of 45 degrees. Okay, so for sine of 2 degrees, I'm just going to look and make sure my calculator's in degrees. It's in degrees, great. And then I'm going to do sine, so I'm going to do sine of 2. Just like that. Sine of 2 in degrees. And then I'm going to press enter, and I'm going to get 0.0348. It's going to give you some decimal. I'm going to say it's approximately 0.0349. For cosine of pi over 5, I'm going to change the mode to radians. And then I'm going to do cosine of pi over 5. So let's see, quit. So cosine of pi divided by 5. Just like that. Sorry, can you guys see that? And look, I'm in radians. You can see the rad up there. When I do that, let's see, I get 0.809. Great. Now, what about tangent of 2? Is that radians or degrees? Well, if there isn't a degree symbol, it's radians. So there's a couple on the homework that are like this, where some people often think it's degrees. It's only degrees if you have that little circle symbol that means degrees. So I'm going to do, let's see, tangent. Where'd you go, tangent? Tangent of 2. I'm going to get about negative 2.185. Now you might notice that there isn't a cosecant button on a lot of calculators. To do cosecant, you really have to do 1 over sine of 45 degrees. And if you do that on your calculator, depending on the calculator, you might get you might get this to be approximately 1.414, but you might also get this to be equal to just the square root of 2. For special angles, sometimes calculators are smart enough to know that that's actually what you want. So check it out. If I do 1 divided by sine of 45 degrees, mode degrees. So here's my 1, where I'm doing 1 over sine of 45, and it gives me just the square root of 2, because my calculator is smart enough to know that that's what it is. But if you then did the approximate button, it would also be 1.414 approximately. I should mention, my calculator does not have a cosecant button. Oops, sorry. It has an inverse sine button, right? Sine to the -1. That is not cosecant. That is the inverse sine function. Just how like logarithms and exponentials are inverse functions, sine and inverse sine are inverse functions. If I tried doing inverse sine of 45 degrees, if I do that, it does not give me, right? It doesn't work. So it's definitely not the same thing as 1 over sine. So be careful, right? Sine -1 is not 1 over sine. It's the inverse sine function. Okay. So that's all the calculator stuff. Let's talk about some special angles. So there are 2 special triangles that have 3 special angles involved. The first one you get by cutting a square in half. So let's say I've got a square, side length of 1. I'm going to cut it in half diagonally. It's a right triangle. And I don't really need the rest of the square there. I can find the length. Well, first of all, I should say each of these angles is 45 degrees, right? I took a 90-degree angle and cut it in half. So it's 45 degrees. Or if you prefer, pi over 4 radians. And then we can find the third side here by using the Pythagorean Theorem. 1 squared plus 1 squared equals c squared. 1 squared is 1, 1 plus 1 is 2. So 2 is c squared, so c is the square root of 2. And we don't approximate that, we just leave it as the square root of 2. So then I want to find all the 6 trig functions of this special angle 45 degrees or pi over 4 radians. So I want to find sine of pi over 4, cosine of pi over 4, tangent of pi over 4. And the other ones, I'll write those in a minute. So sine of pi over 4, and so in this triangle I can use either angle because these are both the same. So 45 degrees is pi over 4 radians. So sine of pi over 4 is opposite over hypotenuse. Or it's opposite over hypotenuse. Either way, it's 1 over root 2. Now, usually we rationalize our trig values here. We multiply this by the square root of 2 over the square root of 2. And what's square root of 2 times square root of 2? It's just 2. And 1 times square root of 2 is square root of 2. So usually we say sine of pi over 4 is root 2 over 2 instead of saying it's 1 over root 2. But either way would be correct. It's just that we usually rationalize. Cosine is the same. Right? Cosine of pi over 4 is, or pi over 4 is adjacent over hypotenuse, which is also 1 over root 2, which we rationalize as root 2 over 2. And tangent of pi over 4 is opposite over adjacent, which is 1 over 1. Or tangent of 45 degrees is opposite over adjacent, which is 1 over 1. And then we can find the rest. And this is where I always kind of run out of room. So cosecant of pi over 4 is hypotenuse over opposite. So cosecant of 45 degrees or pi over 4 is hypotenuse over opposite, which is root 2 over 1, which is just root 2. Right? It's really just the reciprocal of 1 over root 2, which is root 2 over 1, which is root 2. And then the same thing is true for secant. Secant of pi over 4 is hypotenuse over adjacent, which is root 2 over 1. And finally, cotangent of pi over 4 is the reciprocal of tangent, which is just 1. Or it's adjacent over opposite, which is also just 1. So the thing I always keep in mind about the angle 45 degrees or pi over 4 radians is that for that angle, and only that angle, or angles like it. Sine and cosine are the same. And tangent and cotangent are the same. And secant and cosecant are the same. It's kind of the only angle where that happens. Okay. So that's one of our special triangles. People call this the 45, 45, 90 triangle. Whoop, I didn't draw it. That's not a very good drawing of it. Right, so it's the 45, 45, 90 triangle. And the sides are 1, 1, root 2. Or more generally, the sides are some length x, and some length x times root 2. Right? These sides are always in that proportion. If these sides are the same length, x and x, then this side is that length times the square root of 2. Okay, let's look at our other triangle. Let's see. Okay, cool. We're good. I'll make sure I get all this said before class is over. So our other triangle is, where'd you go? Oh, sorry. Yeah, it's a 30, 60, 90 triangle. So, oh, sorry, I forgot to say how we get this triangle. So that you get this triangle is you take an equilateral triangle where all the angles are 60 degrees and all the sides are like, I'm going to say they're like 2 to make it easier. And we cut it in half. So if we cut that angle in half, it's a 30-degree angle. That's a 90-degree angle. That's a 60-degree angle. This side is 1. This side is 2. So this side is 1. This side is 2. And this side here, we're going to find. So using the Pythagorean Theorem, this side here, a squared plus 1 squared equals 2 squared. Solving for a squared equals 2 squared minus 1 squared. A squared equals 4 minus 1. A is the square root of 4 minus 1, which is 3. So this is going to be the square root of 3. Okay. So we can use this triangle to find sine all the trig functions of 30 degrees or 60 degrees, which is, I should point out, 30 degrees is equal to pi over 6 radians. 60 degrees is equal to pi over 3 radians. Because I do want you to get used to writing things in radians, because we do things with the radians a lot. So let's find the 6 trig functions of pi over 6. So sine of pi over 6, cosine pi over 6, tangent pi over 6. Let's see, so sine of pi over, so here's pi over 6. Pi over 6, the opposite is 1, the hypotenuse is 2. So you get 1/2. For cosine of pi over 6, the adjacent is root 3, the hypotenuse is 2. So it's root 3 over 2. And tangent is opposite over adjacent, which is going to be 1 over root 3. We rationalize that, and we multiply by root 3 over root 3 to get root 3 over 3. Right? 1 times root 3 is root 3. Root 3 times root 3 is 3. And then the other 3 are the reciprocals. So cosecant of pi over 6 is going to be the reciprocal of that, which is 2, or 2 over 1. And then secant of pi over 6 is going to be the reciprocal of that, which is 2 over root 3. We do rationalize it. We multiply it by root 3 over root 3 to get 2 root 3 over 3. And finally, cotangent of pi over 6 is the reciprocal of this, which is root 3 over 1. Or it's adjacent over opposite, which is root 3 over 1. All right, let's do the other 6. So now we're going to do sine of pi over 3, cosine of pi over 3, tangent of pi over 3. So here's the thing. We're still using the same triangle. We're just now looking at that angle. So for this angle, the opposite is root 3 and the adjacent is 1. And the hypotenuse is still 2. So sine of pi over 3 is going to be opposite of our hypotenuse, which is root 3 over 2. Cosine of pi over 3 is going to be adjacent over hypotenuse, which is 1 over 2. Tangent of pi over 3 is going to be opposite over adjacent, which is root 3 over 1. And then the reciprocals we can do again, right? So cosecant of pi over 3, the reciprocal of this, well, we already did that before, right? The reciprocal of root 3 over 2 was 2 over root 3, which we rationalized as 2 root 3 over 3. And secant of pi over 3 is the reciprocal of 1/2, which is 2. And cotangent of pi over 3 is the reciprocal of this, which is 1 over root 3, which we rationalize as root 3 over 3. So now here's what I'll say about these. You definitely want to get these down. I would encourage you to try to memorize these triangles. They come out a lot. They come up a lot. These angles come up a lot. And typically, what we really usually remember is we usually remember the 3 primary ones, and then we remember the reciprocals as the reciprocals. So if I'm asking for cosecant of pi over 6, I'm like, well, I know sine of pi over 6 is 1/2, so then cosecant is the reciprocal, which is 2. Same deal here. You might also notice that for these angles, the sine and the cosine values switch. Right? Sine of pi over 6 is 1/2. Cosine of pi over 3 is 1/2. Cosine of pi over 6 is root 3 over 2. Sine of pi over 3 is root 3 over 2. So there is definitely a connection there to be. And that's actually true for any angles that are called complementary, where the 2 angles add up to 90 degrees. If you have complementary angles, the sine and cosine values switch. So sine of an angle is equal to cosine of the complementary angle. Sine of 30 degrees is equal to cosine of 60 degrees. Or cosine of pi over 6 is equal to sine of pi over 3. Kind of neat. So lastly, right, how do we find, so there's a couple things I just want to say. If you have to find these. And so if I was going to try to find, if someone asked me just out of the blue, what's secant of pi over 4? Well, I would say secant is the reciprocal of cosine. So it's 1 over cosine of pi over 4. And then I know that cosine of pi over 4 is root 2 over 2. So this is 1 over root 2 over 2. But then when you divide by a fraction, you flip and multiply. This is really 2 over root 2. Now, there's a long way and a short way to do this. The short way is when you divide anything by its own square root, you get its own square root. I'm going to say that again. When you divide any number by its own square root, you get its own square root. It makes more sense maybe if it's like a number that's actually nice. Right, what's 9 divided by the square root of 9? Well, that's 9 divided by 3, which is 3, which is the square root of 9. You could also rationalize, though. You could say, oh, this is 2 over root 2 times root 2 over root 2. And then you get 2 root 2 on top, and the square root of 2 times the square root of 2 is just 2. So those cancel, and you just get the square root of 2. Let me do one more. So let's look at, let's say I want to find both secant, and I know we did these on the other side of the board, but it's good to just do them on there. So let's say I want to find secant and cosecant of pi over 6. So secant of pi over 6 is going to be 1 over cosine of pi over 6. Cosine of pi over 6 is root 3 over 2. Again, that's something you're going to get better at the more you practice it. This is 1 over root 3 over 2. You flip and multiply. So we get 2 over root 3. And then we rationalize. We multiply by root 3 over root 3 and get 2 root 3 over 3. And then we can also do cosecant of pi over 6. It's going to be a little bit easier. That's going to be 1 over sine of pi over 6. Sine of pi over 6 is 1/2. 1 divided by 1/2 is 1 times 2 over 1, which is just 2. other small thing I should say. This isn't in any of your homework questions, but I do want to point it out because I don't think we say it anywhere else in this class, and it does come up in future classes. Two angles are coterminal. If they differ by 1 or more full revolutions. So for example, 30 degrees and 390 degrees are coterminal because their difference is 360 degrees, which is 1 full revolution. Or 60 degrees and 780 degrees are also coterminal because their difference is 720 degrees, which is exactly 2 full revolutions. Or pi over 4 and 9 pi over 4 are coterminal because their difference is 8 pi over 4, which is 2 pi, which is 1 full revolution in radians. So that's what it means for two angles to be coterminal. Basically means if you draw them, they end up in the same spot, right? Here's 60 degrees, and here's 780 degrees. Let's see, there's 360, there's 720, there's 780. So yeah, two angles are called coterminal if they end at the same terminating, that's why the coterminal, same terminating ray.